Hello, everyone. Okay, so let's wrap up chapter 8. I'm not sure if I'll finish all of it, but maybe we will. And that'll probably be the extent of what will be covered on the second exam. Okay, so orbital filling diagrams and Hund's rules. So sometimes it's useful to illustrate these configuration diagrams in an orbital diagram so we can see the relative energy levels of the 2s and 2p. And I believe I did put... I guess I didn't put that diagram in here. Okay. So how we fill out these diagrams is that each diagram shows the spin of the electrons. So remember, each electron can only be spin up and spin down. So we should only fill 2 arrows of opposite spins in each of these spaces here that represents the orbitals. So for example, we're only going to consider the valence shell. So for boron, we'll have 2s and 2p. There's 3 valence electrons in boron. So we're going to fill out the 2s first, then fill out the 2p orbital at the top there. How about for carbon? Now we go to 2s2, 2p2. So now let's omit the 2s orbital. Well, I think I meant to put... Okay, no. So for carbon, we have we can place the second electron in either the same orbital or with a single electron in both of in 2 of the p orbitals and leave 1 empty. So which one's correct? Well, Friedrich Hund, not Hund. Found that the most stable arrangement of the electrons can be predicted from the following set of rules here. So those are the rules that we're going to follow as well. So these are known as Hund's rules. So 1 electron is added to each orbital in a subshell before any 2 electrons are added to any orbital. In the subshell. So before we pair electrons, we add 1 electron to each orbital in the subshell. So then electrons are added to a subshell with the same spin until each orbital in the subshell is occupied with 1 electron of the same spin. Okay. So it's kind of maximizing the amount of spins you have in the subshell. So in this case, we'll go with example 2 on the right in this picture above. Okay. So these rules are a consequence of spin and repulsion of electrons. So you can't, you shouldn't pair up electrons because there's going to be an orbital of higher, there's going to be an electron. So it's more energetically favorable to avoid electron repulsion. So it's better to fill out an empty orbital because there's no electron repulsion, because there's no other electron in the orbital, rather than pairing up the electron with another electron in the same orbital. Okay? So according to Hund's rule, we should place the 2 electrons in the p orbital for carbon in 2 different orbitals, like we see here. When we get to nitrogen, we add another electron to the empty p orbital. When we get to oxygen, we start pairing up and filling up the orbitals of the 2p. So filling 1 of the p orbitals, the 9th electron fills the 2nd orbital. So now we have 2 paired orbitals, and then lastly we paired the last orbital with neon. Okay, so that's Hund's rule and electron configurations. So we'll spend more time in discussion filling out these diagrams and also writing electron configurations, okay? So we'll get more practice with that. All right, so let's talk about the last 2 sort of periodic trends here. So next week we'll start talking about Lewis structures, and I'll talk about one more periodic trend for chapter 8, and then that will be it. But there's three of them we want to cover. We already talked about ionization energy, so that was one of them, one of the most important ones. Now we're talking about atomic radius. So atomic radius, we will talk about atomic radius and electron affinity. So electron affinity is related to ionization energy, but it's kind of the opposite process. All right. So for atomic radius, there are a number of ways to define it. But generally, we say it's half the distance between the nuclei of two adjacent atoms. So there are several ways we can define this depending on the interactions of the atoms. So first, we have a covalently bonded compound, chlorine gas, where the atoms get close to each other, where their spheres kind of overlap. So that overlap gives a chemical bond, right? So orbital overlap. So that's called the covalent radius. So the radius would be half the distance between the nuclei of two like atoms joined by a covalent bond in the same molecule, such as chlorine, the chlorine molecule. So we're talking about the metallic radius. It's somewhat similar. It's half the distance between the nuclei of two adjacent atoms in a pure solid material. So see how the metal atoms are arranged in an orderly fashion? So that's what solids look like on the particulate level. So we probably won't have time to talk about solid materials, which is a very important field, by the way. But sadly, we have to cover other things that are kind of like more important towards the degrees you students are trying to achieve. So we'll actually have to put materials probably on hold for now. But if you do take a material science class, you would learn all about this, about how different materials are composed, the properties, like what kind of arrangement of the solids in the solid state do they have. So it's a very interesting concept, a very interesting topic. But sadly, in general chemistry, we have to cover a lot of things, and some things will just have to be left out naturally. Okay. So that's for metallic radius. Such as aluminum, sodium, copper, stuff like that. So the van der Waals radius is half the distance between the nuclei of two like atoms, like argon. Okay. So in the gas molecule, there's not really, but if you have solid argon, this would be the radius between of two atoms, but not metallic atoms. Okay, so like this will be for like a non-metal, such as like argon. Okay, they're packed, but they're not bonded. So they're not bonded, right? Argon doesn't form a bond, but they're packed together in a solid state. So that's the van der Waals radius, which they're attracted to each other because of something called the van der Waals force. But we won't talk about that until chapter 11, which is probably the last chapter we'll cover in this class. Okay. And then D is we see the description between the covalent radius versus the van der Waals radii of chlorine. You see, chlorine, the van der Waals radius is a lot larger than the covalent radius, and that's because in the van der Waals radius they're not actually bonded, so the distance between the two spheres there is going to be larger, or the radii is going to be larger than, say, a covalently bonded molecule. All right. So using this idea for radii, we can actually quantify the radii of atoms. So in general, as we see in this table, the atomic radii decreases as we move from left to right. So the opposite trend of ionization energy. Okay. So this is due to the differences. Remember the core charge on atoms? So the effective nuclear charge experienced by the electrons in the valence shell is going to be a lot different than the so there's going to be, so depending on what row of the periodic table you are, the force of attraction is going to be different for the valence electrons, and that explains the relative sizes of these atoms. Okay, so electrons further from the nucleus, remember we said they feel less of the nuclear charge on the from the protons, so they'll actually feel less. It'll take less energy to remove those electrons, and in turn, the size of the atom generally increases because as you go down the periodic table, the size of the atom increases as you add new energy levels to the atom. So it's getting increasingly further away from the nucleus, thus the size increases. Okay, and so what happens is that what's happening is that the nuclear charge is being kind of shielded by the inner electrons, so they cover the nuclear charge from the outer electrons, and that allows the outer electrons to kind of expand the size of the atom. So as they get further away from the nucleus, they're held less tightly to the core of the atom, so the size increases. Now, as you go across a row, you're adding electrons to the same energy level, so there's no shielding effect. So you're actually as you add more electrons, you're adding more protons for the element, and then when that happens, you're going to the electrons in the energy level that you're adding electrons to as you move across left to right, the force of attraction is going to increase, so it actually contracts the electrons, or it contracts it has a higher pull on the electrons, and that overall contracts the size of the atom. So the more protons you have and the more electrons you have, as you go across a row, the size decreases, and that's because of the nuclear charge experienced by the electrons. Okay? So what about ions? What's the trend of ions? So the trend of ions is a little bit different. So you see here, as we go to more positively charged ions, as you go to a more positive charge, the effective nuclear charge is greater because there's less electrons to shield it. So you're going to generally decrease in size as you go from higher charges. So you see here the sizes for the +1 ions are relatively larger than the +2, +3, +4 ions. And then once you get to the negative ions, it tends to get larger. And that's because once electrons are added to the same energy level, you get a point where you're adding more electrons than there are protons, and that electron repulsion will pretty much disrupt the nuclear charge, because now the electrons, since there's not enough protons to pull on all the electrons are going to cause repulsion amongst the other electrons in the atom, and that causes the effective nuclear charge to kind of weaken, because it's outnumbered now by the number of electrons, and that causes the force of attraction on these new electrons to be less. Thus, they're allowed to kind of move further away from the nucleus, or they're not held as tightly compared to the neutral element, and that causes the size to generally increase. So in general, anions are larger than their neutral atoms, and then cations are smaller than their neutral atoms. And the trends are kind of related to the nucleus and its effective pull on the electrons. When you have more protons, the pull is stronger, your atom decreases because they're pulling on the electrons more tightly. And then once you get to an anion, you add more electrons than protons, and that causes the electrons to feel less force of attraction because there's now not enough protons to hold all the electrons tightly. Okay? And if we look at some diagrams here, we see here if we compare potassium to K plus, its weight is smaller than its the neutral element, and then so for sulfur, the anion is much larger than the neutral element. So why is this the case? And we look at these graphs here, we can clearly see this trend here. The positive ions are smaller, and then the negative ions are larger. And why is this the case? So cations typically have more protons than electrons. So the effective nuclear charge will increase, and like I said, the force of attraction will increase for the electrons in the ion. Because since now there's a excess of protons, the extra electrons that were shielding other electrons are gone. The electron repulsion decreases, and the force from the nucleus will now hug the electrons more tightly and bring them closer to the nucleus, and this will contract the atom. So just like I said before, anions now have more electrons, so the nuclear charge will be more distributed to more electrons. So on average, the nuclear charge will feel less force per electron. Okay? So this causes electron-electron repulsive forces, and this will also interfere with the attractive forces to the nucleus, and like I said, weaken it. So this will result in a decreased attractive force and smaller force of attraction per electron. Okay, so the electrons are now held less tightly by the nucleus, and this will cause electrons to kind of expand in the energy level and be held less tightly, and that will cause the size of the atom to expand or increase. Okay? All right, and we can see that this data here represented by this graph if we plot it. All right, so the last thing we'll do is compare the sizes of neutral sodium and chlorine atoms with their ions. Okay. So compare the sizes of neutral sodium and chlorine atoms. So if we look at our graph here, for sodium, we have 190 picometers. So sodium all right, so 190 picometers for sodium atom. And then for the ion, we see that it decreases, right, to 102. And then for chlorine, the chlorine atom, the atomic radii is 79 up here. So 79 up here. And then for the chlorine ion, we see that the it's increased to 181 picometers. Right here. So there's chlorine, there's sodium. See, the trend is opposite here. Sodium decreases when it goes to the ion. So sodium, so cations are smaller, whereas anions are larger. So that is something to consider when arranging the atomic size of atoms and ions, because that's something I like to ask as well on exams. So please keep that in mind. So I like ionization energy, and then I also like atomic radii. Okay, so let's stop there for today, and then next week we'll wrap up the last trend, which is electron affinity, and then we'll start talking about Lewis structures, chemical bonding. So chemical bonding and drawing Lewis structures. Okay, so I think a much more applicable and exciting topic Well, I don't know. I think quantum has is interesting in its own way, but I prefer drawing molecules and investigating chemical bonding. And without quantum mechanics, that wouldn't be possible. So, without understanding the nature of the electron, now we do, and now we're going to see what happens when we can combine the wave functions of two electrons, or combine the orbitals of of electrons on two atoms to form a chemical bond. So I'll see everyone next time.